Okay, so in this video, we're going to take a look at uncertainty. There's a few things we're going to look at. So we're going to talk about what uncertainty actually is. We're going to look at how we estimate the uncertainty and some common measurements we might take. We're then going to look at fractional and percentage uncertainties with a view to looking at how we determine uncertainties in calculated values as well. So let's make a start. All right, so if we start off with what uncertainty actually is. So the first thing to establish that no measurement is exact. It doesn't give you a definitive value for what a quantity's value is. What it does is it gives you a range of possible values that the quantity could have. And that range of values is what we call the uncertainty. So just to give you a quick example to show what I mean, here we're using a ruler to measure a pencil. So to us, when I'm looking at this, it looks like the length is around about 16 centimeters. But when we're using a ruler, we'd say, or maybe it could be as low as 15.5. It's definitely over the halfway mark in this, but where it is, to be exact, we don't know. And it's going to be less than 16.5. So that's how we're getting to 16. We're essentially rounding down from 16.5 or up from 15.5. So we've got this range of possible values that its length could be, and that means it has an uncertainty of plus or minus 0.5 centimeters. So it's 16, but plus or minus 0.5. So that's what we mean by uncertainty. Let's look at a few different measuring devices that we use and the uncertainties that we have with them. So the first kind of uncertainty a measuring instrument has is what we call a rounding uncertainty, sometimes referred to as the intrinsic uncertainty or some other jargon. So essentially, if we've got a stopwatch, you can see on the stopwatch it measures to what it looks like to the nearest 0.01 seconds. So that's what we call the resolution of the measuring instrument, the smallest measurement division you can get. So on the stopwatch, it's 0.01. So we assign the uncertainty of half of that, because essentially what we're saying is anything that's half the resolution above or half the resolution below, they'd all be rounded to the 5.29 seconds. That's the idea. So the first thing with a measuring instrument we have to identify is what its resolution is, or its smallest division. So in this case, that reads 5.29 seconds, so it's 0.01 seconds. So the uncertainty in the time just from rounding is 0.005 seconds, or half the resolution. Now, when we time things, there's more things that contribute towards uncertainty. This is just one of them. Well, that's with a stopwatch. Another example with a voltmeter. So we'll use the same logic here. So the resolution you can see is 0.1 volts. Normally when we use a voltmeter, you probably get 2 decimal places because our potential differences are usually lower than this, but we'll keep it a nice general and have a look at a few examples. So therefore, the uncertainty just to do with rounding is 0.05 volts. What this means is the potential difference could be 96.65, or it could be 95.65. It's somewhere in between those values. So let's have a look at another one which we use to measure angles, obviously a protractor. So looking at this, a protractor has a resolution of 1 degree. Now, a protractor is a bit different to the ones we've met so far because you have to take 2 readings to measure an angle. We have to get the 0 lined up, and we also then have to read off here. So we've essentially taken readings at 2 places on our protractor. So what we're going to do is double the standard value of rounding uncertainty. So the standard value would be 0.5 degrees because it's half the resolution, but because we take 2 readings, we're going to double that. So actually we get the uncertainty is the same as the resolution here, plus or minus 1 degree. Get the same effect with a ruler as well, because again, it takes 2 readings to measure a length. You need the start and at the end. So again, the resolution of this ruler is 1 millimeter. That's the smallest division. So the uncertainty would be 1 millimeter as well. It's twice 0.05 millimeters. Okay, so those are our measuring devices, and just keep an eye out for when we're using two readings. So another example would be a measuring cylinder. We often might do that if we're measuring a change in volume. A thermometer, if we're measuring a temperature change, again, we're using two values to do that. There's a few different scenarios you might come across that. Okay, so we've talked about rounding uncertainty. Now, almost all measurements you will take will include other sources of uncertainty, not just from rounding. And we must account for that in our uncertainty values. So actually the uncertainties are all going to be bigger than we've said they are so far. So when we're measuring length, if we're using a thermometer, if we're using a ruler, if we're using a measuring cylinder, even to a certain extent if we're using a protractor as well, we're going to introduce a parallax error or a line of sight error. So we have to account for this in our uncertainty. So you can see here, by looking at the ruler from different angles, you can see we varied the length by 0.1 centimeters, higher or lower than 4.8. So when we're measuring lengths, we would have to account for that in our estimate of the uncertainty. So here we're introducing about another 0.1 centimeters. So the length uncertainty would be plus or minus 0.2 centimeters. And that now includes both the parallax uncertainty and also the rounding uncertainty. And those are the main two uncertainties that affect length measurements. We might introduce more if we're not able to get the ruler right next to something. So if our ruler's a bit further away, that might introduce some more uncertainty. If we're trying to measure a curved type shape, that might introduce more. But most standard length measurements, these are our two uncertainties that we have to factor in. Another scenario where there is more uncertainty than just the rounding uncertainty is when we're timing stuff using a stopwatch. So if I'm timing the same event, so we have something that takes exactly the same amount of time each time. If I sit there with a stopwatch and time it, I would get a variation of about 0.2 seconds. So that means whenever I, as a person, am measuring the time for something, I will introduce an additional uncertainty of 0.2 seconds. So overall, combining together all the uncertainties, we'd say that timing with a stopwatch has an uncertainty of 0.2 seconds. And the reason we haven't included the rounding in there is that the 0.005 seconds is just insignificant compared to that. So we don't even bother thinking about it because it's, 100 times bigger or so. So it's not even worth considering that. So when you're timing things, a thing to bear in mind is if you can find a way to remove the human from timing, you're going to make your uncertainties a lot less. Okay? So things like using light gates and slow motion cameras are always going to be sensible modifications to experiments. Okay, so here's a table kind of summarizing our typical measuring instruments and the uncertainties that they have. So with a ruler, as you said, so our rounding uncertainty is twice the resolution because we take two readings. We also will have, as much as we try and avoid it, there will be some kind of parallax uncertainty in as well, usually about another millimeter. So we usually say lengths have an uncertainty of 2 millimeters. In some scenarios, we might increase that, but that's a very typical value we use. Stopwatch, rounding uncertainty is pretty insignificant, but the human uncertainty from using a stopwatch is going to be the main contributor here. Thermometer, again, its basic rounding uncertainty would be about half the resolution, so 0.5. But then once we take into account parallax, that probably gives us about another degree, so it's about 1.5. Protractor, similar kind of logic. Protractor takes two readings, which is why the uncertainty is the same in the resolution. Parallax probably introduces about another degree into that, so we've probably got plus or minus 2 degrees. So just to flag these up, these are all kind of back of the envelope guesswork. So these are all approximations or estimates, but they're like pretty decent ones. With a voltmeter and ammeter, it depends which setting of you are using them on. So what I've done here is do the settings we typically are using. If we're using the milliamp scale, obviously this is going to change. If we're using the high range potential difference setting, that's going to change, but this is our typical one. So with a voltmeter and ammeter, what you typically find is you get some flickering. And I'll expand on that in a second, but essentially it doesn't settle on a fixed value. It's sort of oscillating between a range of different values. And so what we'd do is we'd add on the uncertainty for that, which would be about half the range of the flicker, which means our total uncertainty is going to be varied depending on the scenario. For a second. So this crops up when we're using the more precise settings on the voltmeter ammeter typically. And what you get is the value is flickering. So what we have to do is pay attention to the range of values. So let's say our voltmeter is flickering between 96.2 and 96.8. So to get the uncertainty from the flickering, what we do is say, well, the flickering has a range of 0.6. So that's going to give us an uncertainty of plus or minus 0.3. Because we're essentially saying it's flickering about the point 96.5, and it could be 0.3 higher and it could be 0.3 lower. So that's going to give us a total uncertainty of 0.35, including the rounding uncertainty. So this is just a specific example. Depending on the experiment and the scenario you will get different ranges of flickering, so you'll get different uncertainties, but that's how we deal with it. Okay, so those were all ways of estimating the uncertainty. What we might want is a bit of a better way of getting an idea, what is the actual uncertainty in this particular scenario? And we can do that as long as we've got repeat readings of the same quantity. So let's say we're doing an experiment, I don't know, we're measuring a time, and we'd have repeat readings of time because we as humans would expect we're going to get a range of different readings because we're not very good at timing. So let's say we've got here, so we've taken 3 repeats, we've got an average, and then on the right hand side you can see we've worked out what the uncertainty in the time is. And just to show you how that was done, so what we do is halve the range of values for the same thing. So what does that mean? Well, in the first row, those 3 times are all measuring the same thing. So the uncertainty is going to be the biggest minus the smallest, that's the range, which we then halve, and then I've rounded it up. So with uncertainties, something to get in the habit of is we always round up because we're always trying to be a bit conservative with our uncertainty calculations. So we'd actually get 0.025. I've rounded that up to one significant figure here. So that is the uncertainty. That's where 0.03 has come from. Now, one thing I flagged up down here in red is this: we got the same value every time we repeated, and so that by this calculation gives us an uncertainty of 0. So that should be a party for us, right? We've got no uncertainty. Well, actually, no. We never think that something has an uncertainty of 0. So that's a key point to take away here. So if we were to calculate a value of 0, what we would do is we'd assume it to be equal to the rounding uncertainty. So if we're measuring times to 2 decimal places, what we would do is go, nope, this is not 0, it's actually 0.005, which is our rounding uncertainty for a stopwatch. So uncertainty is never 0. We might need to substitute in that particular case. Okay, so now we've looked at how we can estimate the uncertainty in a measurement of one thing. What we might look to do is compare the uncertainties in different things, or even combine them together in some sort of calculation. So first of all, why might we want to compare uncertainties? Well, if we're doing an investigation and we're trying to minimize the uncertainty in the investigation overall, the thing that it makes sense to do is target the thing that's the biggest contributor to uncertainty. And this method will allow us to do that. So fractional uncertainty is calculated by taking the uncertainty in a value and dividing it by the actual value itself. So with a voltmeter, we said once we'd combined all of the different uncertainties together, the rounding, the flickering, we said earlier this had an uncertainty of 0.35. This clearly has a value of 96.6, or whatever the value it's flickering about is. So we can see it's got a fractional uncertainty of 0.004. Now that number in itself doesn't really have any meaning. It's only when we compare it to something else that this will actually have significance. If we want to turn that into a percentage, which we sometimes do, we can just times that by 100 and we've turned it into a percentage. So you can see we've got 0.4%, which is actually, in the context of experiments done in a typical school lab, is a pretty good value to get. If we're getting less than 1, we're onto a winner there. Okay, so that's how we calculate fractional and percentage uncertainty. So how would we do that if we've got our uncertainty and stuff from repeat readings? Well, again, we're going to calculate fractional uncertainty in the same way, but in place of the value, what we're doing is we're putting the average in here. Okay, so that's the value that goes in, and our uncertainty is obviously the range over 2. And then if we want percentage, again, times it by 100. So you can see that with these times, we've got a percentage uncertainty of 10%. So that's actually pretty big, and that would be something we'd want to deal with in our experiment. So why is this fractional percentage useful? So if we just compared the uncertainties, we might go, well, the voltmeter is 0.35, stopwatch is 0.03. And we've gone, well, the voltmeter is much bigger than the stopwatch, so we should get a much better voltmeter. And that would actually have been the incorrect conclusion here. We can't compare this value here, the 0.03, and this value here, the 0.35, because they're measured in different units, and the values which they're associated with are completely different. So this is where we want the fractional. So this is for the time over here, and we get the fractional percentage. So this is for the potential difference. So you can see here that if we compare the percentage uncertainty, say, time is 10%, whereas the potential difference is only 0.4. So clearly we need to do something about our time measurement. Maybe we want to use light gates for a slow motion video. Maybe that would help us improve that. But that's the key. If we want to know our biggest contributor, we have to work out our fractional or our percentage uncertainty, and whichever you use, it doesn't really matter. Okay, so that's what we might use them for. The final thing we might use fractional or percentage uncertainty for is if we're trying to determine the uncertainty in a calculated value. So let's say we measure an angle to be 20 degrees, and let's say we estimate its uncertainty of 1.5 degrees, just like we had in the table earlier. So the question is, well, what would the uncertainty in the sine of that angle be? Well, there are two methods, I think, for doing this, and neither's really better than the other. They're both getting at the same thing. So method one is we say, well, the fractional uncertainty in sine theta is the same as the fractional uncertainty in theta itself. Okay? So that's an assumption we're going to make. So if we go, okay, well, the fractional uncertainty in theta is 1.5 over 20. And sine theta, its value is 0.34. So if we want to get the uncertainty in sine theta, we're going to take its fractional uncertainty and times it by the value, because essentially we want 34% of that's a complete myth. We want 7.5% of 0.34 essentially. That's what this calculation is doing. And once we do that, we find our value, and we get the uncertainty in sine theta is about 0.03. And sine theta doesn't have any units, so I haven't given a unit for the uncertainty. So what that means is sine theta is 0.34 plus or minus 0.03. That's one way we could do this. Now, the other way we can approach using a sort of maximum and minimum method. So we go, well, what is the sine of the biggest this angle could be? Well, it could be 20 plus 1.5, so it could be 21.5. And we can do the sine of the lowest value, sine of 18.5. Once we've got this, that tells us our biggest value and our smallest value. So if we do range over 2, you can see it gives us our uncertainty in sine theta as 0.02. So again, what this means is that sine theta, so in the previous page we actually calculated what it was because it was sine of 20 plus or minus 0.02. So you can see these two methods gave slightly different estimates for what the uncertainty is, but that doesn't matter. These are all kind of approximate methods, so the fact that they give you slightly different answers isn't a problem. The fact that the answers are really close tells us basically those methods doesn't make any difference which one we use. So either of those two is absolutely fine. So what if we're doing something with our measurements? What if we're going to do A times B? So let's say A is a time, and it's 0.6 seconds plus or minus 0.2 seconds, and B is a length, 2.1 0 meters plus or minus 0.02 meters. Very typical values and uncertainties. Well, the key piece of information we're going to use is that the fractional uncertainty in A times by B is equal to the fractional uncertainty in A plus the fractional uncertainty in B. So essentially, their uncertainties in the fractional sense are adding together to give you more overall uncertainty. So here's our fractional uncertainty in A. Here's our fractional uncertainty in B. So the fractional uncertainty in AB, or A times B, is just those two added together. But we wanted to know what the uncertainty was. So we're going to need to calculate the value of AB and multiply it by the fractional. So this is our fractional. The actual value of A times B is 0.6 times 2.10. That's going to have a very obscure unit of seconds meters. I put it as seconds meters, so we didn't mix it up in milliseconds. And then if we want to know what the uncertainty is, we take the fractional, times it by the value, and that tells us it has an uncertainty of 0.4 seconds meters. So what does this mean? It means AB is equal to 1.3 plus or minus 0.4 seconds meters. Now, why did I round to 1.26? Well, if our uncertainty is in the first decimal place, we can't possibly be giving a second decimal place. That's just nonsense. So I just rounded the value up to 1.3, and it's plus or minus 0.4. So essentially, it's between 1.7 and 0.9. Okay. We want A times B. What if we wanted A divided by B? Well, the structure is the same. We're still going to add together the fractional uncertainties. So even if our operator changes and now it's a divide, we're still going to add together the uncertainties. And the logic behind that is the more different measurements we use, they're each going to introduce their own uncertainty. So the uncertainty overall is always increasing. So if we have the fractional uncertainty in AB, which is what I calculated previously, it's going to be exactly the same. We now need to calculate the value of A divided by B, which now has the unit of seconds per meter. And then we're going to do the fractional uncertainty times by the value. That gives us our uncertainty here. So essentially, what this means is A divided by B is going to be 0.3 plus or minus 0.1 seconds per meter. Again, I've done the same thing. I've rounded the A divided by B to one decimal place because the uncertainty is in that position column there. So it could be 0.2 or it could be 0.4. If the uncertainty in the value of AB cubed, so we've introduced a power here. Well, essentially, what we're going to do is we're going to multiply the fractional uncertainty by the power, which is why you can see the fractional uncertainty in B is multiplied by 3. So if your value is raised to a power, multiple the fractional uncertainty by that power, because essentially B is contributing to uncertainty 3 times, because you've used B times B times B. So you've got 3 sets of that uncertainty. And then the way you go about it then is the same thing. So we've got the fractional uncertainty, then we've got the value, and then we're doing the fractional uncertainty times by the value, giving us an uncertainty of plus or minus 2 seconds meters cubed. So what that means is that AB cubed is 6 plus or minus 2 seconds meters cubed. Again, the decimal places are just irrelevant because we've got plus or minus 2. There's no point saying 5.6 plus or minus 2. It's just nonsense. We've got plus or minus 2 there. Okay, so hopefully we've covered each of these things. So now the questions to ask yourself is, can you actually describe what uncertainty is? Do you know how to estimate the uncertainty in each of the common measurements, like using a ruler, stopwatch, those kind of things? Can you calculate fractional and percentage uncertainties? And can you determine the uncertainties in calculated values? And that's what I'm hoping you're able to do now you've had a chance to watch this and have a think about it.